Lecture 3, Vision, Stimulus, and the Optical System.
Welcome back. In Lecture 2, we talked about the distinction between sensations and perceptions. We identified the brain as the organ of perception, and we talked about some factors that can influence brain functioning and the change that this brings about in our perceptual capacities. Lecture 3 marks the first of a series of lectures where we actually look at the different sensory systems and identify the ways that which receptors change physical energy from the world around us, that is, sound or light or touch or smell or taste or pain or what have you, changes these physical sensations into the language that the brain understands, namely electrical impulses. You see, the brain itself is totally unresponsive to light or sound or touch. The brain doesn't even experience pain, and the reason for this is because the brain possesses no receptors. So the brain receives information from all of the sensory systems, but the brain itself only knows what the receptors tell it. The brain is only sensitive to electrical impulses. So our receptors act as the transducers, the interface between the physical world and the brain. We're going to start our discussion of the sensory systems with the visual system. That's not quite an arbitrary decision. It turns out that most people, if you ask them what their most important sensory system is, they will say the visual system. So it's traditional in textbooks of sensory psychology and what have you to start with the visual system. Actually, it's not a unanimous belief that the visual system is our most important sensory system. For example, Helen Keller, who, as you may recall, was both blind and deaf, felt that deafness put her at more of a disadvantage than blindness. Helen Keller wrote that blindness separates you from things in your environment, but deafness separates you from other people. The medium of language being unavailable to somebody who is deaf. So the other organisms that would disagree that vision is the most important sense are virtually all other organisms but people. It turns out that phylogenetically speaking, that is across the phylogenetic scale, the chemical senses are much more important than the visual senses. There are no animals that don't possess some form of chemical sensitivity, smell or taste, or a combination of the two, called the common chemical sense. But there are plenty of animals who don't have vision and or hearing the way we do. So phylogenetically speaking, vision is not the most important sense. And there are some people who think that maybe deafness is more harmful to our interactions with other people than blindness. In any event, we're going to start with a discussion of the visual system. I propose that first we talk about the nature of the physical stimulus. What is it that the visual system responds to? And your answer would be, well, it responds to light. What do we mean by light? Well, it turns out that light is electromagnetic radiation. But not all electromagnetic radiation is light. We'll get to that in a minute. Electromagnetic radiation was first discovered and measured in the late 1880s by a physicist named Heinrich Hertz. Professor Hertz was the first one to generate radio broadcast waves, which are a form of electromagnetic radiation, and the first person to measure them. And we'll have a little bit more to say about Professor Hertz at a later time in the course. Anyway, light is electromagnetic radiation. Now, the full spectrum of electromagnetic radiation is incredibly long, going from the X-rays, which have a wavelength of 1 nanometer, which is 1/1000th of a meter. So we have 1 nanometer at one end, and at the other end we have the radio broadcast waves with a wavelength of 100 meters. So it's incredibly broad. Of that full spectrum of electromagnetic radiation, the part that the human eye is sensitive to is known as the visible spectrum, and it only extends from 400 nanometers to 700 nanometers, a very infinitesimal portion of the entire electromagnetic spectrum. Now, let me alert you, modern science has a bit of a quandary, a bit of a problem in dealing with the physical stimulus for light, because in most instances, it is convenient and informative to think of light, of electromagnetic radiation between 400 and 700 nanometers, as traveling in continuous transverse waves, the kind of thing you would see if you threw a rock into a pond and the waves would ripple out. On the other hand, some of the characteristics of light are best understood if we think about light as traveling in discrete packets. For example, if a photography is using a light meter to measure light intensity, the result may well be expressed in photons. Photons are thought of as discrete packets of energy, discrete packets of light. So some aspects of light are best understood by thinking of transverse waves, and other aspects, namely the brightness, the intensity of light, is best understood if you're thinking in terms of discrete packets of energy. So don't let that throw you. It's just a little something we have to deal with. Okay, the visible spectrum extends from 400 nanometers to 700 nanometers. The 400 nanometer end is called the short wavelength end. The 700 nanometer end is the long wavelength end. The short wavelength colors of the visible spectrum are the blue-violet colors. The long wavelength end are the reds, the orange and reds. So we can replicate an experiment done by Sir Isaac Newton in the late 1600s, where Sir Isaac passed a beam of white light. White light is made up of all of the colors of the visible spectrum. Passed a beam of white light through a prism. And he then displayed the light reflected out of the prism on a viewing screen. And what Sir Isaac discovered was that when you pass light from a medium of one density, namely the air, through a medium of another density, namely the glass of the prism, that the different wavelengths of light from 400 to 700 have different indices of refraction. They bend different amounts as they pass through the prism. And so what comes out the other end, we pass white light into one side of the prism, and coming out the other side is the visible spectrum ranging from high frequencies of wavelength to low, so that we see coming out the other end red, orange, yellow, green, blue, indigo, and violet. And that is always the order of the visible spectrum from high to low. Whether you're looking at a rainbow or whether you're looking at a rainbow effect that occurs when your neighbor is misting his or her lawn, or whether you look at the sunlight reflecting off an oil slick in the street, red, orange, yellow, green, blue, indigo, violet, from high to low wavelengths. There's a simple mnemonic device to remember the order of the visible spectrum. Just remember the name of the fictitious character, Roy G. Biv. Roy, R-O-Y, red, orange, yellow, G, green, Biv, blue, indigo, violet. Okay, so now we know that the visible spectrum goes from 400 to 700 nanometers, that the blue end is the short wavelength end and the red end is the long wavelength end. Let's talk about some other physical properties of light. For example, we know that the speed of light is an incredible 186,000 miles per second. That is absolutely incredible. A beam of light, if you were to stand on top of a mountain and flash a beam of light, it would travel around the circumference of the Earth 7.5 times in 1 second. You know, I can't even talk about the speed of light without, against my will, thinking about the astronomical unit, the light year. A light year, of course, is the distance that a beam of light will travel going at 186,000 miles a second in a year. And the closest star to our solar system is 4 light years away. It would take a beam of light 4 years to get to the closest star to our solar system, traveling at 186,000 miles a second. That's why I never took any astronomy classes in college. My brain can't comprehend it's like trying to comprehend the national debt or Bill Gates's bank balance. Light years blow me away. In any event, the speed of light is so great that compared to the speed of light, the speed of sound is laughably slow. The speed of sound being 1110 feet per second. So sound is traveling at 1110 feet per second and light is traveling at 186,000 miles per second. And this leads to some practical considerations. I remember as a Boy Scout, we were taught that we could estimate the distance from us that a lightning storm was doing its mischief if, when we saw the flash of lightning, we began counting 1001, 1002, 1003, 1004, 1000. If you got to 1005, we knew that the storm was about a mile away, because, of course, a mile is 5,280 feet, and the sound is traveling at 1110 feet per second, and the lightning you can consider instantaneous. Now you can keep track of the course of the storm. Is it coming toward you or moving away from you? Another practical consideration of the enormous difference between the speed of light and the speed of sound can be seen in events like the Olympics. Prior to 1960, the sprint events were started by a starter's pistol. Runners take your mark, get set, go, bang. Somebody analyzed years and years of Olympic records, and they found that the people in the lane closest to the starter pistol were winning just a little bit more frequently than you would expect by chance. And it turns out that at that level of excellence, even the slight advantage of being a little bit closer to the starter pistol gave the people in the near lane an advantage, both in the swimming events and in the running events. And so, beginning with, I believe it was the 60 Olympics, instead of using a starter pistol to start the sprints, either swimming sprints or running sprints, each competitor got an individual beeper under his or her starting blocks. So now, all's fair in the Olympics, both swimming events and running events, because the difference in the speed of sound vis-a-vis the runner in the first lane and the runner in the far lane has now been removed as a factor. Okay, what else can we say about the physical stimulus? You now know the visible spectrum and you know the speed of light. Let's talk about the miraculous instrument that responds to light and changes it into electrical impulses so that the brain can be aware of what's going on. And that, of course, is the human eye. Now, the lecture will be most meaningful if you have access to a lateral view of the anatomy of the eyeball, because we're going to be talking about some of the structures in the eyeball. What we are going to do is divide the structures in the eyeball into three categories. The eyeball contains what I'm calling supporting structures. It's including neural elements, and it's including the receptors. What I want to do first is talk about the supporting structures. Probably in lecture 4, we will talk about the receptors and the neural elements in the visual system. The supporting structures in the visual system are elements that in and of themselves do not lead to the release of neurotransmitters and do not lead to the release of electrical impulses. Rather, the supporting structures make the visual stimulus more accessible to the receptors. An example of supporting structures in another sense may help clarify what I mean by supporting structures. In the sense of touch, the hairs on your skin are certainly not receptors and they're not nerve fibers. They are supporting structures. It turns out that they amplify light touches and make this light touch more accessible to the receptors. That's what I mean by a supporting structure. In the visual system, the supporting structures do things to the light to make it a more attractive stimulus for the receptors. Let's take a hypothetical beam of light and pass it through the eyeball, and we'll talk about the supporting structures that this hypothetical beam of light encounters on its way from the front of the eye to the back of the eye. If we shine this hypothetical beam of light into the eye, the first structure that this beam of light encounters is the cornea. The cornea is an example of a supporting structure. It doesn't generate electrical activity, and it doesn't release any chemical transmitter substances. The cornea is what we call a fixed optical instrument. Okay, so we pass this beam of light through the transparent cornea. The next supporting structure that our beam of light encounters is the pupil of the eye. Now, the pupil of the eye is actually a hole in the iris. The iris is that part of the eye that gives it its characteristic color. When we talk about eye color, so-and-so has blue eyes or brown eyes or green eyes, we're actually talking about what color their irises are. And of course, the iris color is an inherited characteristic. Now, the iris has the interesting capability of increasing or decreasing its opening, which we call the pupil, by some ciliary involuntary muscles. In very, very dim light, the pupil may actually open up because of the iris, the muscles in the iris. The pupil may actually open up to a diameter of 8 millimeters. On the other hand, in very, very bright light, the pupil may narrow down until it's only about 1.5 millimeters in diameter. Now, what is the benefit of this? Well, in very, very dim light, the eye opens up to its full extent to give us access to the relatively sparse level of illumination to make it more likely that we will detect objects in our environment. In very, very dim light, the pupil narrows down to 1.5 millimeters in diameter to keep from overstimulating the sensitive retinal elements with a light that is perhaps dangerously bright. Just for completeness, let me mention that there are other circumstances besides the ambient light intensity that determines pupil size. A researcher by the name of Eckhard Hess, about 30 years ago, discovered that pupil size is also influenced by whether you like or dislike the thing you are looking at. I don't have time to go into how Hess hit upon this, but it's an interesting story. In any event, he did an experiment, where he measured pupil size by keeping people in a level of illumination that kept the pupil not in its totally open state, not in its totally closed state, so that he could measure changes in either direction. And he showed them different pictures. This was around the time that a scary shark movie was playing in the theaters. And when he showed people a picture of a shark, their pupils tended to get smaller. When he showed people pictures of cuddly, chubby, gorgeous little babies, their pupils tended to get larger. He also was moved to do an actual experiment on pupil size, thinking that it might actually serve as an index of a form of nonverbal communication that may take place below the level of our awareness. Very quickly, he got a group of male subjects, and he told them that they were involved in a project on problem solving. Go into the next room and pick a female partner. In the next room, Hess had twice as many females as he had males, and he had treated randomly half of these women with atropine sulfate, which dilates the pupil.
Lecture 4, Vision, the Retina.
Welcome back. In Lecture 3, we talked about some of the physical characteristics of the visual stimulus, the characteristics of light that give it its particular color, and we talked about the supporting structures and the job that they do in giving visual acuity such a boost. Now we're going to talk about some of the elements on the retina, namely the receptors and the neural elements. Whereas the supporting structures make vision more acute, the receptors and neural elements make it possible. Without them, we would have no vision. Let's start by talking about the receptors. The human eye is described as having a duplex retina. This is because we have actually two types of receptors on the retina at the back of the eye. As most people know, or many people know, these two receptors are called the rods and the cones. These two categories of receptors have different functions. They look different, they have different names, and they contain different photopigments. So let's elaborate on some of that. Of course, rods and cones are named because of their physical appearance. Rods are tall and rod-like. Cones are shorter and cone-like. So they call them rods and cones. But there are more important differences than that. They have different functions, and they have different numbers in the retina. Rods, for example, not only are they bigger, but they are far more numerous. There are approximately 120 million rods in each human retina. Each eye has 120 million rods and only 6.5 million cones. So rods far outnumber cones in the human visual system. Rods are also found in a different spatial location from cones. If we view the eye as a sphere, and of course the front of the eye is taken up with the optical instruments, so the posterior 2/3 of the eye contain the retina. And the rods and cones, of course, are found on the retina. On the retina, rods are found out in the periphery of the visual system. They're out on the edges. As we move toward the center of the eye, the number of rods drops off until we get to the macula, which is the middle portion of the eye, that part of the eye that you focus on when you want to read the fine print. The peripheral macula still has a few rods, but it's mostly cones. And in the very middle of the macula, we have an area known as the fovea, which we will talk about at a later time. The fovea is 100% cones, no rods. So rods are found out in the periphery and cones are found in the macula. And this is because of the important functions that each of these two categories of receptors mediate. Let's start with the rods. Rods function very well in dim light. They don't need a whole lot of light to see, which means that our peripheral vision is that part of the visual system that operates better in dim light. They are also very good at detecting movement, far better than the cones. For example, I'm going to hold my finger out in front of me, and then I'm going to slowly move it around, focusing straight ahead, and I'm going to move my finger until I'm no longer aware of it. Now, if I want to become re-aware, all I have to do is wiggle it, and the movement jumps out. Rods are very good at detecting movement in dim light. The problem with rods is that they do not perceive color, and that's why our night vision is only in black and white, because the rods, which are functioning in dim light, do not perceive color. The other problem with rods is they don't have very good acuity. You would never dream of reading something by holding it off to the side because the rods don't have good acuity. The cones, on the other hand, do have great visual acuity, which is why we use central vision to read fine print. Cones also have the benefit of permitting us to see color. Cones mediate color vision, rods do not. The downside of rods is they don't, of cones is they don't work well in dim light, and they're not that great at detecting movement, especially in the periphery. So we have two aspects of the visual system. One that is good for color vision in normal levels of illumination and having good acuity, and the other mediating the vision of movement, the perception of movement in dim light out in the corners of our eyes. Both rods and cones operate by virtue of the fact that they contain chemicals known as photopigments. The rod pigment was discovered about 150 years ago because if you take an animal that has a rod-cone visual system, such as people, well, you wouldn't do this with people, but the rhesus macaque monkey has a color vision system identical to the human's eye. So if you get a rhesus macaque retina and you squeeze it out, and you squeeze all the goo out of it, mostly what you're getting is the rod photopigment, because rods are bigger and they outnumber the cones. So it was possible 150 years ago to examine the rod photopigment. Now, when you pour it in a test tube, it was purple in appearance, so they first started calling it visual purple. They then changed its name to rhodopsin, which is the name for the rod photopigment. When you shine light on a test tube of visual purple, the stuff changes color right in front of you. It bleaches from purple to gray. Now, in a test tube, it stays that way. In the visual system, it regenerates back into visual purple, which is why we can keep seeing over and over again, whereas in the test tube, it bleaches once and it's finished. The photochemical process that occurs when you shine light on a photopigment is called bleaching. It's actually a chemical change. We know some things about rhodopsin from these early studies. We know that it is maximally sensitive to a wavelength of around 500 nanometers. Now, because rhodopsin, which is found in all the rods, is found in a structure that does not have color vision, the rods don't know that 500 nanometers is a bluish green. The cones can perceive 500 nanometers as a bluish green, but the rods see it in terms of lightness and darkness because they don't have color vision. The cones possess three separate photopigments. There are three categories of cones. One cone contains a photopigment that is maximally sensitive to 419 nanometers, which is a blue. Now, these three categories of cones have overlapping spectral sensitivities. So a blue cone might also be able to see red and green, but not as well as it sees blue. One pigment is 419 nanometers, which is a blue. This is found in some cones that we call the blue cones. Other cone pigments contain a photochemical substance, a photopigment that is sensitive, maximally sensitive to 531 nanometers, which is a green. And some cones possess a photopigment that is maximally sensitive, that is bleached maximally by 558 nanometers, which is a red. So we have what is called a trichromatic color system, because our visual system can match any color that the human eye is sensitive to by signaling to the brain the relative amount of blue, green, and red that particular color excites by virtue of how much excitation it produces in the three categories of cones. Rods are unable to perceive color because there's only a single rod pigment, and you need mixtures of activity in different pigments to produce color mixture in the brain. So that's it. The rods are out of luck in that regard. Color blindness or color weakness occurs when a particular cone pigment is either totally lacking, which is rare, or deficient, which is much more common. So our visual system, as I said, is called a trichromatic visual system. Now, only animals that possess both rods and cones are capable of color vision, and not all animals do. For example, the cat has an all-rod retina, which is why the cat doesn't see color. The cat has an all-rod retina. It can tell shades of lightness and darkness, but it can't see the array of hues that the human visual system is sensitive to. The benefit of the rods, as I said, is that they can let us perceive movement in dim light. Now this was of greater practical significance in earlier decades than it is presently. For example, in both World War I and World War II, they didn't have the sophisticated tracking devices and radar and sonar and what have you that they have now. So if a sailor was standing night watch on a battleship, they were told, if you hear the droning of an airplane engine, look off to the side of where you hear that droning, because at night you're much more likely to detect in dim light something moving with the rods than with the cones. So practical use was made of this as soon as it was discovered that the rods are better at detecting movement in dim light. Hundreds of years ago, astronomers also made use of the different functions of rods and cones, in that if an astronomer expected some astronomical event and they knew in what quadrant of the sky to look, they would look off to the side, giving themselves a better chance to detect this event. So the rods and cones then complement each other. Acuity versus sensitivity, movement versus color. They've each got something to add to our visual ability. An interesting, I find it interesting anyway, point about animals with all rod retinas. You can not play a trick on them, but for instance, in earlier decades in psychology, most experimentation was done on the albino rat, which has an all-rod retina. Now, the problem with doing experiments on rats is that they are nocturnal creatures. They prefer to be active at night and to sleep during the day. So the people who are training these rats would prefer to sleep at night and be active during the day. How do we get the rat to cooperate? Well, what we do is change the rat's day-night cycle. What we do is remove all the light bulbs in the colony room and in the testing chamber and replace them with red lights, because the rods do not see red. 500 nanometers is too far from 558 nanometers, and the spectral sensitivity of rhodopsin does not extend to 558 nanometers. So when you have a red light on, the rat thinks it's dark. You can come into the laboratory, turn the red lights on, the rat says, it's dark, it's time for me to be active. Now the human eye can see nicely in red light. So we train the rats and run them in mazes or do whatever we want to do with them. And then when it's time for us to go home, we turn the red light off and we turn the overhead lights on and leave them on all night. So the rat says, it's light, it's time for me to go to sleep. So we make the rat adapt to our sleep and wakefulness cycle by using red lights in the day and white lights at night. By the way, there was also a practical significance to the rods not seeing red, again harking back to World War II. Fighter pilot aviators who were flying a night mission, or bomber crews that were flying a night mission, needed to dark adapt to be as visually sensitive as possible. And the way that you dark adapt is you sit in the dark for 45 minutes and let all the rhodopsin regenerate. Now, if you're going out on a night mission and you may be shot down or killed, or you're going to be nervous, and here you have to sit in a dark room for 45 minutes. Well, it was discovered that you can dark adapt pilots very nicely by putting red goggles on them, which the rods don't see, and letting them wait for their turn to take off, being in the ready room with their buddies where they can talk or play cards or do anything they want. The rods don't see red light. They only see lightness and darkness, and they only see if the stimulus is in the vicinity of 500 nanometers. I know this seems odd, but that's the way it works. Now let's talk a bit about the neural elements. There are two layers of neural elements on the retina in addition to the receptors, the rods and cones. These two layers of neural elements are called respectively the bipolar cells and the ganglion cells. Now, before I get into the contribution that the bipolar and ganglion cells make to vision, let me share with you that because of the presence of a layer of bipolar cells and a layer of ganglion cells in front of the receptors, and if you have a diagram of the eyeball, this would be a good opportunity to take a glance at it. A beam of light enters the eye, passes through the cornea, through the pupil, through the lens, and then before it can get to the receptors, it must go through a layer of ganglion cells and a layer of bipolar cells. This appears to be a serious design flaw with the retina. In fact, the human retina is described as an inverted retina because it looks as though it were designed just backwards. You would think it would make more sense to have the light first strike a receptor, then strike a layer of bipolar cells if you need them, and then a layer of ganglion cells. And the axons of the ganglion cells form the optic nerve and take the information to the brain. But that's not the way the human eye is designed. In fact, I read just recently, as you may be aware, there is renewed interest in this debate between proponents of intelligent design and proponents of the Darwinian evolution position. One opponent of intelligent design said, look at the human eye. What is intelligent about that? You've got bipolar and ganglion cells blocking light from reaching the receptors. Well, there may be other examples of lack of intelligent design in the design of the human body, but that's not one of them. It turns out that the way the human eye is designed is the only way it would work. Because of the fact that these visual receptors operate by bleaching when light shines on them and regenerating when they get a chance, they have high metabolic needs. And the only way that the visual receptors can in fact continue to bleach and regenerate continuously is if they are actually in physical contact with their nutrient source, which is a highly vascularized layer right behind the receptors known as the pigment epithelium. The visual receptors must be in physical contact with the pigment epithelium to get the energy they need for this constant bleaching and regeneration that underlies the transduction process. So the fact that we have an inverted retina is a great compromise. The visual system is about as sensitive as you could get given the constraints that they must be in contact with their blood supply for energy needs. Anyway, we do have these two layers of neural elements, the bipolar and ganglion cells. Let me give you some approximate numbers to make a point, not just to fill your head with trivial information. We know that there are 126 million receptors, 120 million rods, 6.5 million cones. There are 50 million bipolar cells and 1 million ganglion cells. So what we have is 126 million receptors being stimulated by light, bleaching, generating electrical impulses. Those electrical impulses are fed to 50 million bipolar cells, and then the 50 million bipolar cells in turn feed their information to 1 million ganglion cells. The 1 million ganglion cells have long neural processes known as axons, nerve fibers, which then go back through the bipolar cell layer and through the retina and form the optic nerve and go on to the brain. So if time permits, I will talk a bit about this, but where the optic nerve, where the 1 million axons of the ganglion cells squeeze out of the eyeball, they push the rods and cones out of the way so that each eye actually has a tiny blind spot, which many of you may be
Lecture 5, Vision, Beyond the Optic Nerve.
Hello and welcome to Lecture 5. In Lecture 4, we talked about some of the functional differences between rods and cones and the way rods and cones interact with the neural elements, the bipolar and ganglion cells, and how this interaction results in the periphery of the visual system having greater sensitivity and the central region, the macula, especially the fovea, having greater acuity. Today we're going to continue a discussion of the visual system, talking about the way two different broad categories of visual perception are analyzed at different levels of the visual system. One of these categories of visual perception is more primitive. It is innate. That is, it's based on the maturation of pre-existing nerve circuits, and it's located in subcortical regions of the brain. The other category of visual perception is of a higher order nature. It depends more on learning and experience, and it depends upon the integrity of neural circuits in the visual cortex. Let's start out talking about the more primitive category of visual perception first. Let's give it a name. Let's call it object location. Object location refers to the perceptual ability whereby we can be aware of the existence of objects in space around us without giving it conscious thought and not know exactly what these objects are, but just have a sense that they're out there. For example, I can detect something to my right. I don't really know what it is. I look and I see it's a door. So object location is known to depend upon midbrain circuits. Now, let me give you a quick anatomy of the brain lesson. The most primitive part of the brain, evolutionarily speaking, millions of years older than the rest of the brain, is the hindbrain. Now, the hindbrain does little more than keep us breathing and keep our blood pressure up and what have you. It's concerned with the vital functions. It doesn't do anything intelligent. It just sits there and keeps us alive. About 1 million years after the hindbrain, another layer of cells grew over it that we call the midbrain. This is the level at which object location is managed, at the midbrain level. The midbrain actually has two broad classes of responsibilities. One, it maintains our level of sleep, wakefulness, and arousal, so that midbrain damage will put you in a deep coma. The other important role of the midbrain is to mediate reflex orientation to sensory stimuli, and here's where object location comes in. The midbrain actually mediates reflex orientation for more than just visual stimuli. For instance, if I'm walking down the street and a car backfires, midbrain circuits cause me to orient toward it. I don't stop and think, hey, what was that noise? I better look. I'm already turning before I'm consciously aware of the car backfire. The midbrain has the capacity to cause us to center sudden unexpected stimuli, get it on our midline. So I hear the noise and I'm lining it up with the midline. If a flash of light occurs over here, I don't stop and think, gosh, should I look and see? I'm already orienting toward it. Also for touch, if I'm walking down a dark alley and something taps me on the shoulder, I don't stop and think, maybe I should turn around and see who that is. Maybe I know this. No, I'm already wheeling around midbrain stuff, and then thinking comes later. Okay, now the part of the midbrain that is especially responsible for visual orientation, orienting to visual stimuli and being aware of visual objects in the field, is known as the optic tectum. Now, tectum is a Latin word meaning roof, and it turns out that this part of the midbrain that's responsible for orienting to visual stimuli or being aware at some primitive level of where they are in space around us, it's on the top of the midbrain, or the roof of the midbrain. Thus, it is called the optic tectum. Now, in addition to mediating our awareness, a primitive awareness of where things are in space with regard to our position in space, the optic tectum also makes us especially sensitive to sudden movements in the visual field. So you may be aware of nothing happening and suddenly you detect a movement and you orient toward it. So here are two categories of object location mediated by the optic tectum. One, a primitive awareness of where things are around us without necessarily knowing exactly what they are. And two, a tendency to alert to sudden movement. Now there is a third function of the optic tectum in the context of object location. The optic tectum automatically elicits protective responses of a duck and cover nature if the visual system detects something moving rapidly toward us. Let me give you an example of such a phenomenon that I experienced a few months ago. In our house, my wife likes flowers in the appropriate season, so we have hanging baskets around the front porch and around the back porch, and it's my job to water them every night. And what I usually do is I take the hanging baskets down, and I hose them and give each plant its full measure of water and then put them back up. One night we got home late. My wife wasn't looking. I was going to take a shortcut. I filled the watering can, and I'm going to run from basket to basket and just give it enough water to kind of get it through the night. Okay, so I'm watering one basket, and I'm reaching. I can't really see what's in it, and all of a sudden, something comes hurtling out of that basket, racing straight for my head, and I drop the watering can, and I duck and cover, and I am struck a glancing blow. None of this at the conscious level. I don't have a clue what happened. Then I turn and I watch this thing, and I hear the flutter of wings, and it slowly recedes in the dark, and I realize that a bird had nested for the night in this particular hanging basket, and I was watering the bird, and I startled the bird, and it came racing out of the basket. Narrowly, I suppose it could have done me some harm if it stuck me in the eye with its beak, but the midbrain saved me by causing me to duck and cover. These are examples of object location. You can see that they do not involve any cognition. It's all automatic. It's all reflexive. And they have a protective function. Now, in the other category of visual perception, we called object identification. This refers to our ability to be aware of the fine details of objects around us, not just where they are relative to our position in space, but what color are they? What form are they? What is their identity? What are these things? Are they moving? In which direction? At what rate of speed? Etc. Now, object identification is a very important perceptual ability, and we're going to treat that separately in a later lecture. So I'll say no more about it, except that it does depend upon learning and experience, and it does depend upon the integrity of the occipital cortex, the primary visual cortex at the back of the brain. Now, it is possible to see a dissociation between object location and object identification. These two categories of visual perception, which go together in most cases in normal human beings, can be dissociated, and we can see this in two situations. We can see it in the case of human patients who have experienced brain damage involving the occipital lobe. And we can also see it in certain animals whose visual systems do not extend beyond the level of the midbrain. There are such animals. Let me talk about the human situation first, where we can see a dissociation of object location from object identification. Patients with occipital lobe damage are blind. They report their visual fields to be dark and empty. They do not see a light if it's shined in their eyes. They are blind. Now, picture this situation. This phenomenon is called blind sight that I'm about to describe, and it sounds like it couldn't be real, but it is. You can take one of these blind people. Now, this will not work if your blindness is due to degeneration of the retina or severing of the optic nerve or something like that. This can only be demonstrated in people whose blindness is due to cortical damage at the cerebral cortex. Okay, you sit such a person at a table and you say to them, there is an object on this table in front of you. Please reach out and grab it. Now the people think you're fooling them, and some of them get a little bit angry. What do you mean? You know I'm blind? No, please humor me. Please reach out and try and grab the object. Now finally you can convince them to go along with this, although they think it's absurd, but they reach out and lo and behold, they touch the object, and they are startled. They have no idea they were about to touch an object. Blind sight. They don't know what it is until they feel it. These people identify objects by touch, not by sight, and they identify people by the sound of their voice or by their odor if it's somebody they know very well. But they have no functioning vision. at least none that they're aware of. But they can reach out, with their eyes open, of course, and touch objects on a table in front of them. Or you can do another, you can put them in an empty room with one object, and they can say, the experimenter can say, there is an object in this room. Can you point to it? And they say, of course I can't point to it, I'm blind. Humor me. Try and point to the object. And they say, oh, okay. And lo and behold, they point to the object. So what is happening here is that these midbrain object location circuits are still intact. But because they operate without awareness and without volition or cognition or intelligent input of any kind, the people are unaware of their existence. They still have no object identification. They don't know what things are, but at some primitive level, they know where they are, but they're not even aware that they know where they are, suggesting that some aspects of perception can take place without awareness. Now, very quickly, I will tell you that I was personally involved in a demonstration of what I now know is blindsight in cats in the late 1960s. I was engaged in a research project studying recovery of function following damage to sensory parts of the cerebral cortex, and one group of cats had been prepared with extensive brain damage in the visual cortex. They were, for all intents and purposes, blind. They had to be lifted out of their cages, and they had to be put in front of their food, and they were blind. Now, I had at that time an animal caretaker who was a very caring person. He was going to be a veterinarian when he graduated from school, and he cared very much about animals. Now, I remember instructing him. I said, Nick, this bank of cages contains blind cats. Let them out for exercise, but let them out one at a time so that you can monitor them and they don't bump into things because they're blind. Well, I came to the laboratory, to the colony room unexpectedly one day, and Nick had about 6 of these blind cats out at the same time. And I said, Nick, I asked you not to let all the cats out at the same time because you can't monitor them and they can get hurt. He says, Doc, I've been working with these cats for months now. They never bump into anything. And I thought, oh boy, I wish you had listened to me, because one of the cats was taking off at a good trot and it was running straight for a wall. And I thought, this cat is going to break its nose. But just before it ran into the wall, it stopped, leaned forward, and smelled the wall. I saw another cat running for a table. We kept the cat food up off the floor for sanitary purposes on a table, and he was running straight for a table leg. Instead of banging into the table leg, the cat stopped, and he leaned forward and he rubbed on it. They looked like they were trying to investigate what this thing was that they just didn't run into. Somehow these cats were able to avoid bumping into things, but they looked as though they didn't know what it is they had just avoided bumping into. And it's now clear to me that this was sort of a cat version of blind sight. They didn't know what was around them, but at some primitive level they could keep from bumping into it. Okay, object location and object identification then are the two broad categories of visual perception. Both of them require another ability, the ability to perceive depth in the visual field, depth perception. In the case of object location, it's clear and obvious. In order to locate something in space, in order to be aware of its position, you have to know how far from you it is. So you can see there that that object location would involve an ability to perceive depth. In the case of object identification, it's a little less obvious why you need to have depth perception to identify things, but let me give you a quick example. Part of object identification is knowing what these things are. It turns out that a toy automobile about 3 feet from you would take up the same space on the retina, would subtend the same visual angle, to put it in more technical terms, as a real car 70 yards away. Now, your ability to tell that one is 3 feet away and one is 70 feet away, 70 yards away, would be important in proper identification of which one is the toy and which one is real. So depth perception turns out to be an important part of both object location and object identification. Now, it turns out that just as in the case of the two broad categories of visual perception, object location and object identification, one is more innate and one is more based on learning, the same is also true of depth perception. There are two categories of depth perception cues that we use to judge the distance from us to objects in the visual field. One of these categories of depth perception is more innate unlearned, based on neural circuits that are present at birth and only depend upon maturation. And the second category of depth perception cues is, in fact, based more on learning and experience. Let's talk about the more primitive category of depth perception first. This is a category based on what are called binocular depth cues. Now, binocular means depth cues that require the simultaneous use of both eyes. Binocular depth cues, there are several different categories. One is called binocular disparity. Now, the two eyes are about 3 inches apart in a typical adult human. They'll be a little less far apart in a child or an infant, but the two eyes are far enough apart that they each have a slightly different perspective on objects in the visual field. Binocular disparity is based on the fact that the brain is receiving an overlapping image from each eye. There is overlap in the two visual fields. Now, when you're looking at something close to you, the overlap is quite great. As we look at things farther and farther away, the degree of overlap of the two retinal images is slightly different. The brain is able to calculate the degree of overlap from the left eye and the right eye and come up with an estimate of the distance that we are from this object. Binocular disparity. The classic experiment in depth perception in infants was done by a developmental psychologist by the name of Eleanor Gibson. Let me give you the punchline first. Experiments on children and infants suggest that binocular depth cues are in place and usable by infants by the time they're 3.5 months old. By the time an infant is 3.5 months old, this infant is able to use retinal disparity to gauge depth. Now, let me tell you about Eleanor Gibson's classic experiment.
Lecture 6, Vision, Age-Related Changes.
Hi, welcome to Lecture 6. In Lecture 5, we talked about the two broad categories of visual perception: object location, which is mediated by the optic tectum, and object identification, which is mediated by the visual cortex. Before I get down to business and talk about age-related changes, which is the topic for Lecture 6, let me just elaborate on object location and object identification in light of some tragic events that have recently taken place in South Florida. 3 young women have recently been killed by alligators. Now, alligators are an example of one of those creatures that does not have any visual system above the level of the optic tectum. And so what we know now is that alligators are working with pretty good object location capabilities, but not very good object identification capabilities, meaning they frequently don't really know what they're eating. They are attracted by movement, and they are attracted by large objects that they can detect, but they really don't have any idea what they're eating, which is why, for example, when they try and hunt down the killer alligator, one way to detect which was the alligator that did the killing was cut them open and see what you find. And sometimes what you find in alligators is fishing boots and baseballs and inedible objects, because anything that moves is fair game. This is especially true because we're having an unusually hot weather season in Florida, and alligators, being poikilotherms, cold-blooded animals, become more active in the heat, and they use up more energy, and they need more food, and they become even less discretionary about what they eat. So the same is true, by the way, for sharks. Their visual system stops at the level of the optic tectum. They are attracted by movement. They're also attracted by jewelry, for example, because remember, the optic tectum causes a reflex orienting to a flashing light, and so the light reflecting off jewelry could attract the attention of a shark. But they're also not sure what they're eating until they actually get a taste of it, which is why sometimes sharks will take a big bite out of a surfboard or a life raft or something of that nature. So yes, they're dangerous, but it's not malicious. They really aren't sure what they're eating. I'm sure they'd much rather eat a poodle than a basketball, for example. But that's what's happening, and we need to be aware that these creatures are dangerous and they're kind of indiscriminate about what they bite. So just stay away from them. Okay, let me get back on track here and let's talk about age-related changes in the visual system. And all of the structures in the visual system do change with age. Let me just start with the iris and the pupil, and then we can talk about the optical instruments of the eye, the cornea, and the lens. The iris, remember, is that part of the eye that gives the eye its characteristic color, blue or brown or green or what have you. With age, the iris begins to lose its color. Now, you may say, big deal. Well, it can be a big deal. The iris loses its color with age because pigment granules begin to slough off the iris. Now, in the anterior chamber of the eye, there is a fluid called the aqueous humor fluid, the anterior chamber being the space between the cornea and the lens. Now, this aqueous humor fluid provides nutrients for the lens and cornea. Aqueous humor is being constantly created. About a teaspoon a day is created, and as new aqueous humor fluid is created, the old fluid drains out through passageways. Now, these pigment granules that slough off the iris can actually help block the channels through which aqueous humor fluid drains out of the eyeball, and so new fluid is being created, and the old fluid is either slow to drain or maybe it doesn't drain at all. And what happens is the pressure, the fluid pressure in the anterior chamber of the eyeball builds and builds, leading to the condition known as glaucoma. So the change of color in the iris can be a problem. In addition to pigment granules, tissue sloughs off the lens and can also contribute to these obstructions in the passageways. When the pressure in the anterior chamber increases above normal, which is it's called intraocular pressure, or IOP. When your IOP gets dangerously high, the pressure is transmitted from the anterior chamber right through the eyeball and can actually lead to damage to the optic nerve and some of the retinal elements. Glaucoma can lead to blindness. So people should be tested for glaucoma regularly. The test is painless and quick, and if that intraocular pressure is too high, corrective measures need to be taken. There is no pain involved in glaucoma, so you won't be aware that you have it unless you get a glaucoma test. Glaucoma is likely to occur in 10% of Caucasians by age 70 and 20% of African Americans by age 70. So this appears to be due, at least in part, to the fact that African Americans are more prone to hypertension, and hypertension is a contributing factor in glaucoma. Okay, so the iris does contribute to the increased likelihood of glaucoma when the pigment granules begin to slough off. Another age-related change in the iris can be seen in the fact that a swelling begins to occur with age right around the border of the iris that surrounds the pupil. Now, what this does is it prevents the pupil from opening to its full extent in dim light, so that what we find is with age, our pupils become unable to expand to the full 8 millimeter diameter that was possible when we were young people. This failure of the pupil to open to its full extent makes it more difficult for older people to function properly at night, and they may have to give up night driving or things of that nature. In some extreme cases, the swelling around the border of the iris becomes so great that the pupil of an older person cannot change its size at all. It stays the same size regardless of the ambient light conditions. Okay, now let's take a look at the optical instruments of the eye, the cornea, which we call a fixed optical instrument, and the lens, which is a variable optical instrument. One age-related change in the cornea that's relatively minor is called the arcus senilis, which, if you translate from the Latin, means the senile ring. Virtually everybody by age 50 can show some early signs of the formation of this arcus senilis. The complete arc is usually not seen until you are in your 60s. As a matter of fact, I checked in the mirror last night for my arcus senilis, and sure enough, I have an opaque ring right around the border of the cornea, where the cornea blends into the whites of the eyes, which are known as the sclerotic coats. There is, in fact, a dark colored ring around the eye. Now, what does this do? Well, it reminds you that you're in your 60s. The other thing it does is it cuts down slightly on your peripheral vision. But basically, it's probably the most harmless age-related change that takes place in the visual system, the arcus senilis. A more, how shall I say, harmful, debilitating change that can take place in the cornea with age is the tendency for the cornea to lose its transparency and take on a cloudy color. Now, when the cornea is young and healthy, it is virtually transparent to all wavelengths between 400 and 700 nanometers. As we age, we are more prone to corneal infections. Maybe we get a scratched cornea that heals with a scar. We're also prone to wart-like growths on the cornea, so that it is possible as we age for the cornea to lose more and more and more of its transparency, and eventually our patterned vision is somewhat impaired. In the case of a badly scarred or clouded cornea, the only alternative is a corneal transplant. This is not such a big deal, really, because corneal transplants are the most effective and least problematic of all of the transplants because they are virtually untroubled by the rejection process. So you don't have to take steroids or things to suppress your immune system after corneal transplants. The reason that the cornea is virtually immune to the rejection process is the cornea has no blood supply. So corneal transplants can, in fact, correct clouded or scratched or scarred up or warty corneas. So when people donate their eyes to an eye bank, the only part of the eye that is useful is the cornea. The rest of the eye, some people think that they can transplant other parts of donated eyes, but it's the cornea that can be transplanted. Okay, so the next optical instrument that I want to talk about is the lens, which we call a variable optical instrument because it has the capability of accommodation, changing its size due to its elasticity. Well, there are 3 age-related changes that take place in the lens. One of them we've already talked about, presbyopia. By the time you're 45, your lens will have lost enough of its elasticity that you're going to have to, for most people, wear reading glasses. Okay. So we know about that one. Another age-related change that takes place in the lens is the tendency to develop cloudy particles in the lens, opaque particles. Now, when you are in your 60s, some degree of this cloudiness is the rule, not the exception. And when this cloudiness becomes serious enough that you have your eyes examined, the diagnosis that you will usually hear is cataracts. Mild cataracts are not serious enough to require surgical treatment. Probably the main consequence of mild cataracts is that you will experience glare in bright sunlight or in bright artificial lighting. Looking at the world through mild cataracts is like looking through a car windshield with a thin layer of road grime on it. You know how when the sun strikes your windshield and the windshield is dirty, you get that glare effect? Well, that's what's happening with mild cataracts, which is why you will see in sunny areas older people wearing peaked caps and walking around with their hands shading their eyes like this because they're experiencing more glare than younger people. When your cataracts get too severe to live with, the only alternative is cataract surgery. There are no eye drops or special diets that will make cataracts go away. You have to bite the bullet and have cataract surgery. It's nowhere near as onerous as it was in earlier decades where they had to make a large incision and cut the suspensory ligaments and pull the cloudy lens out with a pair of forceps. Now the cloudy lens can be liquefied by ultrasound. They bombard it with ultrasonic waves, and then you can suck out the liquefied lens with a suction pipette and put a plastic lens implant in the same location that the lens you were born with used to have. Now the problem is the plastic lens implant can't change its size. It doesn't show accommodation. So if you have a plastic lens implant that's calibrated for distant vision, you're still going to need reading glasses for near work. Some people who perhaps are shut-ins and don't get out much, maybe they would have their plastic lens implants calibrated to read, and on rare occasions when they do go out, they would wear glasses for distant vision. But you're going to need 2 optical corrections with cataracts. Now, the downside of cataract surgery is that in 3% of people who have this surgery, a serious potential consequence is detached retina. Now, I'm going to talk about detached retina in the next few minutes, but I will say that 3% of cataract patients are at risk for detached retina. Okay, the third change that takes place in the lens, in addition to the loss of accommodation, and in addition to the formation of cloudy particles that result in what we call cataracts, is a tendency for the lens to lose its transparency and take on a yellowish hue. This happens in humans. It also happens in cats, dogs, and monkeys. Any older animal, if you do a dissection of the eyeball and look at the lens, an older animal will have a lens with a slightly yellowish appearance to it. The consequence of this in humans is that it tends to reduce our sensitivity to the colors of the visible spectrum across the board. This decrease in color sensitivity is especially evident for the short wavelength end of the visible spectrum, especially the color blue. The blue-violet end of the spectrum is more seriously impaired by the yellowing of the lens of the eye than the red end of the spectrum. This is one of the reasons why sometimes stylishly dressed older women will have a blue appearance to their hair, because they've used some kind of a blue rinse to dress their hair, and their hair is actually bluer than they realize it is, and it's bluer than the older men who hang out with older women think it is. But young people can see that these older women have blue hair, and it's because they have lost their sensitivity to the short wavelength end of the visible spectrum because of the yellowing of the lens. Okay, there are also some age-related changes that involve the visual receptors. And one of these changes is a metabolic change. The visual receptors slow down in their ability to regenerate photopigments, so that while we are aware that a normal, healthy, young human can come out of the bright sunlight and sit in the dark for about 40 minutes and regenerate all of their pigments, and their visual system will be as sensitive as ever, for an older person it's going to take another 10 or 15% in the dark before all of their visual photopigments have regenerated. Now, I mentioned earlier that one of the consequences of cataract surgery in approximately 3% of the people. By the way, that means that 97% of the people who have cataract surgery are not going to have any problem. But for 3%, there is an increased likelihood of, not only an increased likelihood, 3% of them are going to experience detached retina. So let me talk about that just very shortly. Detached retina, the retina of the eye actually begins to peel off the back of the eye, sort of like a curtain being drawn either down or across if the peeling goes from left to right instead of up to down. What's happening in the case of detached retina? Well, remember, there is this fluid in the anterior chamber of the eye known as the aqueous humor. There is also a substance in the posterior chamber that goes from the back of the lens to the back of the eyeball, known as the vitreous humor. Now, vitreous is actually a transparent collagen gel, and it packs the posterior chamber of the eyeball, gives the eye its nice round shape, and it also holds the retina against the back of the eye. With age, there is a tendency for this collagen gel, this vitreous humor, to pull away from its attachment at the back of the eye, making it much more likely that the retina will begin to peel down like improperly glued wallpaper